Welcome to this explainer. Today, we are going to embark on a truly fascinating journey. We're diving deep into the exact mechanics of how we can evolve artificial intelligence from being just a passive thinker, an AI completely stuck inside a standard chat interface, into an active doer, an AI that can actually operate and execute tasks out there in the real world. We're going to unpack the core concepts from Chapter 14 of the Developer's Guide to AI, which specifically focuses on extending agents with tools, and we are going to bring all of these developer concepts to life.
Here is our roadmap for giving AI real agency today. 1. Making AI take action. 2. Writing effective custom tools. 3. The Model Context Protocol. 4. Building an MCP server. And finally, number 5. Testing and complex schemas. Let's just jump right in.
All right, Section 1, making AI take action and breaking out of that chat box. Let's confront the massive limitation that's honestly holding most AI applications back right now. So, we have this fundamental problem of isolation in the AI space. Think about it. On one hand, we have our standard AI. It is an undeniably incredible thinker, right? It can generate highly complex code, write brilliant essays, and analyze just vast amounts of public training data. But it is fundamentally tethered to a chat window. It's like having a genius locked in a room without a telephone. When you ask it to check your actual inventory or update a specific customer record, it just hits a wall. It can't actually do anything with all that intelligence in your specific environment. Now contrast that with the AI as a doer. True agency requires the ability to interact with dynamic resources that a large language model typically cannot access directly. We absolutely want it to be able to autonomously query our local private databases, save files to our local disk, and actually execute real-world tasks in our own business applications. To get from a thinker to a doer, we have to build a bridge.
Well, it turns out the crucial missing link here is tools. To break out of the chat box, AI quite simply needs access to tools. So what are they? Tools are these highly secure, specifically engineered pathways that grant the LLM controlled access to your internal data sources and functionalities. I want you to think of a tool as a tightly bounded sandbox. Without them, the AI is completely unable to interact with the world outside of the massive datasets it was originally trained on. Agent frameworks provide the necessary infrastructure to create these vital connections, allowing the AI to essentially reach out of the digital void and pull a real lever in your actual software stack. It's pretty amazing.
Moving right along to Section 2, writing effective custom tools, the instruction manual. Now that we know what the AI needs to become a doer, let's look at exactly how we build these secure pathways using Python.
Okay, so it all starts with something surprisingly simple in the Python ecosystem, a decorator. Let's say you wrote a perfectly normal, basic Python function to save a text file to your hard drive. On its own, the AI agent has absolutely no idea this function exists, what it does, or how to invoke it safely. But by adding a framework wrapper, like simply placing the @tool decorator right above your function definition, we magically transform that standard everyday function into a rich tool definition. The agent framework steps in, it wraps your code, extracts all the necessary metadata, and exposes it in a structured way so that the AI's reasoning engine can finally comprehend and utilize it. Boom, magic happens.
But you can't just blindly wrap a function with a decorator and expect a miracle. You have to write the underlying function correctly for an AI audience. Chapter 14 lays out 4 golden rules for tool writing. First, use highly descriptive function names. Naming your function process data tells the AI literally nothing, but naming it save customer invoice to database gives it immediate, actionable semantic context. Second, you must include precise type hints for all your arguments and return values so the AI knows exactly what data types are required. Third, write comprehensive docstrings. And fourth, describe every single parameter in plain, natural language. Remember, LLMs are incredibly good at parsing human language, so a plain English description of a variable goes a lot further here than dense technical jargon. Honestly, this illustrates a massive shift in how we have to think as developers. Take a look at this quote directly from the source material. It notes that this description serves as the primary instruction manual for the agent's LLM. Your docstrings, your parameter descriptions, and your type hints, they are no longer just helpful little code comments sitting there for your human coworkers to read on GitHub. No, they are the literal instruction manual for the AI. You are directly programming the AI's understanding of its own capabilities through your natural language comments. If you change a single sentence in a docstring, the AI might suddenly become significantly more or significantly less accurate in deciding when and how to use that specific tool. It's wild to think about.
But here is where we hit a fascinating roadblock. As developers start building more and more of these custom tools, we inevitably run into a massive scaling crisis. It's what software engineers call the N by M problem. Let's say you have 5 different AI agent frameworks deployed across your company, and 50 different custom internal tools. Building custom bespoke connectors for every single agent and tool combination means writing 250 separate integrations. It is incredibly inefficient, brittle, and completely unsustainable to maintain over time. So how on earth do we create a reliable, standardized way to solve this?
Which brings us to Section 3, the Model Context Protocol, or as I like to call it, the Universal Translator. This is a truly revolutionary breakthrough in how we construct these systems. Enter the Model Context Protocol, often just abbreviated as MCP. Think of MCP as the absolute hero of our story here. It acts as a universal translator. Imagine if every traveler in the world needed to carry a separate custom dictionary for every single country they visited. That's the old way. MCP is like giving every system a universal earpiece. Instead of writing custom code for every single agent tool pair, both the agent framework and the custom tools simply adhere to the open MCP standard. They speak the exact same protocol language. This completely eliminates the scaling crisis because developers don't have to worry about the specific technical quirks of every single tool they want to connect to.
So how does this actually work? It builds a very clear, highly robust client-server architecture. Let's trace the flow of communication together. First, at the very top, you have the MCP host. This is the LLM application itself, something like Claude Desktop or your enterprise AI interface, which is actually initiating the communication. Next, inside that application, you have the MCP client, which manages the strict one-to-one protocol connection over the wire. And finally, on the other end, you have the MCP server. This is the external, independent program that is actually housing your custom Python functions and providing those specific capabilities back to the client. The host encounters a user problem, asks the client to reach out, and the server provides the tools to solve it. It is incredibly elegant.
Now, we have to ask, how do the client and server actually transport these messages across the divide? Well, MCP supports a few different transport methods depending entirely on your security and infrastructure needs. The 2 major ones discussed in the chapter are stdio and streamable HTTP. Standard input/output, or stdio, is absolutely perfect for secure local integrations. This is when your agent and your tools are running on the exact same machine, communicating directly via the command line with 0 external network traffic. It's incredibly fast and very secure. But if you're building enterprise cloud applications and you need bidirectional real-time communication over the web between different servers, you would choose streamable HTTP, which leverages server-sent event streams, or SSE. Basically, choosing the right transport mechanism completely depends on your specific business logic and deployment environment.
Once that connection is successfully established, an MCP server doesn't just offer one thing. It actually offers 3 distinct types of components back to the client. The primary one is tools, which we've been heavily discussing today. These are the executable functions that change state, like writing to a database. But the server also offers prompts. These are reusable templates managed on the server side to standardize AI interactions, so you don't have to rewrite complex instructions every single time. And third, it offers resources. Resources are slightly different. They allow the server to provide read-only structured data and context to the LLM, like pulling up an internal API specification document or a static configuration file right before the AI takes an action.
All right, Section 4, building an MCP server and actually implementing this agency. Let's transition from theory into practice and see how we actually build this thing.
Let's get practical. To build a robust MCP server in Python without losing our minds writing boilerplate networking code, we use a library called FastMCP. This library does an immense amount of the heavy lifting for us. It acts as a really powerful abstraction layer that flawlessly bridges the gap between your raw custom Python functions and the AI client making the requests. By handling all the complex protocol negotiation under the hood, FastMCP empowers developers to focus purely on business logic. It allows an AI agent to have a seamless, natural conversation with what would otherwise be a highly technical and rigid tool.
When you first instantiate a FastMCP server in your code, we go right back to those golden rules we talked about earlier. Naming and context are absolutely everything. A vague server name forces the AI to essentially guess what capabilities might be hidden inside.
but giving your server a highly descriptive name, like payroll report generator, alongside clear public documentation passed directly into the instruction parameter, gives the AI vital, overarching context before it even processes a single user command. I like to think of this instruction parameter as the server's public README file. It acts as the ultimate routing guide for the LLM's reasoning engine.
Now, what's really fascinating here is how FastMCP handles the actual tool registration process to save us developers time. To define a tool, you simply apply the @mcp.toolDecorator to your Python function. Then you provide those exact typends we discussed, strictly defining integers, strings, or booleans. And here is where the true developer magic happens. FastMCP automatically parses your Python typends and docstrings and auto-generates a complex JSON schema under the hood. In the past, developers had to write hundreds of lines of JSON schema manually just to explain a tool to an LLM. Now, FastMCP does it instantly. The LLM then uses this generated schema to guarantee it structures its arguments perfectly when invoking your function. It is a massive time saver.
And finally, Section 5. Testing and complex schemas, hardening the build. For our final section, we absolutely need to ensure our newly built tools can survive the harsh complexity of real-world business data.
Up until now in our conceptual journey, we've talked mostly about really simple inputs, right? Like passing a basic string or an isolated integer to a calculator tool. But welcome to the reality of enterprise software development. Real-world business tools don't just pass simple primitive values around. If you are integrating with a CRM or an accounting system, they require massive, complex, heavily nested JSON messages, containing arrays, optional fields, and strict validation rules. If an AI is going to interact with these systems, we need a significantly more robust mechanism to handle and validate this complex enterprise data before it ever touches our databases.
To handle this beast in Python, the chapter introduces Pydantic's base model. By creating a custom class that inherits from base model, for example, let's say an expense class that explicitly requires a date, an amount, and a specific category string, we forcefully validate the data at runtime. This ensures that when the autonomous AI attempts to add an expense or interact with a secure system, its inputs strictly conform to your predictable, predefined business rules. And here is the best part. If the AI happens to hallucinate a wrong data format, say passing a text string instead of a numerical amount, Pydantic catches it immediately and throws a structured error. Often, that exact error can be fed right back to the agent in real time, allowing the AI to realize its mistake and actually self-correct on the fly. It's pretty amazing to watch.
But before we deploy these self-correcting agents into production, we absolutely have to validate the build. And the testing workflow for MCP is incredibly satisfying for a developer. First, you test your expected inputs and outputs by pointing a standard API tool like Postman directly at your MCP server. Because of the standard protocol, Postman will actually generate a user-friendly form based entirely on that JSON schema FMCP generated for you. Once you visually verify in the UI that the schemas are working perfectly and rejecting bad data, you take the final, thrilling step. You natively integrate your custom server with a real-world client environment like Claude Desktop, and you watch your AI seamlessly reach out and actually do the work.
We've covered a massive amount of technical ground today. We moved all the way from the philosophy of simple docstrings serving as AI instruction manuals through the N/M scaling problem, up to standardizing tool access with the Model Context Protocol, and finally, hardening our inputs with Pydantic validation. By engineering proper access to custom tools, we've completely shattered the limitations of the isolated chat box. We really have turned thinkers into doers. So I'll leave you with this final thought to ponder. Now that you know exactly how to give your AI systems real, robust agency, what real-world task are you going to automate first? Thanks for joining me on this explainer. We'll see you next time.